Okay, I can start the introduction. And,
Okay.
it's okay. So, yeah, it's my big pleasure to introduce Rodney Fox's seminar about the simulation of the Grenoble bubble column experiments. As you can see in this document, he has a long list of achievements and awards, but we just mentioned that he's an Armstrong Manson distinguished professor in Iowa State in the Department of Engineering, and since 2022, I think, and he has also been the Fulbright Tocqueville Distinguished Chair and Jean d'Alembert Senior Chair at Paris-Saclay. We are, he spent some time in France during the year, and well, once more, I'm very glad to see this presentation, and I will give you the floor, Rodney.
Okay. Do I need to click share screen or is it automatic?
Yes, I think you need to share.
Okay. Does that work?
For me, perfectly.
Okay,
yes,
it says it's
start.
working. Okay, so so this is a pleasure for me too. We visited Grenoble, I think, with Alberto Batalacqua in maybe 2 or 3 years ago. And Alan and Martin were there, and they asked us if we could simulate their experiments. And so since the last few months, we decided to get serious about this and actually simulate their experiments and compare to the publications that came out last year, mainly in the JFM paper. So I'll start by explaining what the experiments are and the bubble column experiments, and then explain a little bit about the simulations, and then go into some validation data, which we find it be quite good. So pleased to show them. Okay, so the Grenoble bubble column experiments. Here's a picture of the bubble column. It's 40 centimeters in diameter and approximately, I guess, include the top, about 3 or 4 meters high. We took this from their paper. We'll be comparing measurements that are done in mainly the heterogeneous regime, which is from the picture here. You can see it's very dynamic, with upflow of the bubbles and downflow to walls, and very turbulent. The probe that they used is located at the type HS. I think you'll see it later, and they're able to measure bubble velocity statistics, bubble volume fraction statistics, and also liquid velocity statistics. So we compare the same thing for the simulation code. So, okay, so just to give you some background information on the experiments, the fluid they're using is tap water from Grenoble with air as the working gas. Bubble column experiments are usually difficult to compare with CFD codes because of the control of the sparger, but in this case, they used a flat plate at the bottom of the column with distributed holes that give a very uniform injection region at the bottom. In real bubble columns and industrial bubble columns, they usually use a sparger, and then it's very sensitive. At least the first part of it is very sensitive to the how you sparge. So it's hard to do comparisons with the CFD codes, but in this case, it's very nice initial conditions at the bottom of the inlet conditions. Superficial gas velocities that they measured are between 1.3 centimeters per second to 25. Superficial gas velocities measured at the bottom, so it's the average volumetric flow rate then averaged across the cross section. And so 1.3, it's in what's known as the homogeneous regime. Up to 25 is well into the heterogeneous flow regime. As I mentioned earlier, the bubble column diameter is 40 centimeters. The static height, the initial height, is 2 meters. And of course, as you inject in gas, the height goes up substantially as you go up higher and higher flow velocities. The measurement devices are explained in their publications. There are 2 probes. First, the Doppler probe, which is able to measure bubble occurrence and bubble size. So we're able to extract from that the volume fraction. And also simultaneously, they can measure the bubble velocity. So we have information about the joint distribution of void fraction and bubble velocity in the vertical component. And in the liquid phase, they have a Pavlov tube to measure the liquid velocity at the same time as the bubble volume fraction. The measurement section is here at, we'll see it again later, but it's measured here, and we measure from the center line towards the wall. So we'll have data for the across the column radius. For those of you that are not familiar with bubble column dynamics, again, there's two regions. There's a homogeneous region, and in the homogeneous region, you get approximately linear increase in the void fraction of this is measured at the axis with the superficial velocity. And then in a nicely designed bubble column like the Grenoble column, there's a very clean break at approximately 5 centimeters per second, where the void fraction then changes less non-linearly with respect to the bubble volume, respect to the superficial gas velocity. And so it goes up to as high as 40 or 50% as you increase. One way to show the homogeneous regime is to plot the slope. And so you can see in the homogeneous regime, you get a nearly constant ratio between the axial velocity and gas superficial velocity and the axial volume fraction. And then in the heterogeneous regime, you get now a constant slope. Okay, so the data that we'll be comparing to are some 4 papers that came from the experimental campaign. The first 2 are on the probes, and so the Doppler probe, it's a very sophisticated probe. It's able to do phase detection, bubble velocity, and also size measurements at the same time. So this data is mainly in the heterogeneous regime, so that's where I'll be showing you mainly heterogeneous comparisons. Heterogeneous regime around 23 centimeters per second. The second paper is on the liquid phase properties for the bubble column, the same homogeneous and heterogeneous regime. And then the paper that is interesting for our case is conditional statistics of what's known as mesoscale structures. And so what you see in the heterogeneous regime is a segregation according to volume fractions. So you get clustering of bubbles that are moving up. They do not coalesce in this case, but they simply cluster together and move up more faster than zones that have void fractions. And so we're going to be able to look on the measurements. We see this, of course, in the simulations, but this is the first time we have measurements that do the relative motion for conditional velocities given void fraction. And that came out in a JFM paper in 2023. So a lot of the data that we're sharing. So. Okay, so the CFD model uses a two-fluid model that we have been working on. In this case, we're assuming that we have models that do coalescence and breakup, but in this case, it's very nice because coalescence breakup is essentially negligible, and you can see that when you observe it from the experiment that we don't need to keep that into account. The flow itself is going to be like a large eddy simulation in the sense that we're not going to use a turbulence model. There is bubble-induced turbulence generated by the slip velocity of the bubble. We didn't include that. We didn't need that. So we say it's laminar flow, but it's basically 2 sets of Navier-Stokes equations for the 2 phases with no turbulence. So finite volume method. So there is, of course, averaging at the finite volume scale, the lattice scale. Bubble size distribution. So as I mentioned, the data, they are able to actually measure the bubble size distributions, and it turns out that they were, depending on the superficial gas velocity, the bubble size distributions were very tight, and so we do not need to take into account bubble velocity dependent on the size in any one experiment. So we can do a monodisperse case and then use the bubble sizes that were measured from the experimental data. That takes out one unknown, which is trying to predict bubble size distributions. For the gas, we do include let the gas expand as the hydrostatic pressure changes, although it's very small. And for the liquid, we used to use a constant density, constant temperature condition for liquids. So we see our inlet conditions are very simple. We have a flat plate sparger, we have an inlet boundary condition, and then we use the same height as in the experiments for the initial water filling. And then the outlet, well, we have a much higher column than we need for the outlet to keep the flow from arriving at the top at the maximum flow velocity. Okay, for drag models, if you're familiar with bubble column simulations, there are a lot of drag models that are available, but the most reliable is the one by Akio Tomiyami, and so we're using his model. In our case, the Ethos number is such that the bubbles remain nearly spherical, so it's mainly controlled by the Reynolds number. We're using a lift model of Tomiyami for the bubbles, again, spherical bubbles, and then we need virtual mass, constant coefficient. And to be sure that the system is hyperbolic, we need a turbulent dispersion term or some other term. And so we're using the model that we developed for turbulent dispersion. Not really a turbulent dispersion, it's a term that depends on the volume fraction gradient. But it's called turbulent dispersion in the literature. Okay, for the solver, we're using OpenFOAM. So this is Alberto Passalacqua. Passalacqua is an OpenFOAM expert, so we use almost all the simulations are done in OpenFOAM. The version number is for version 3 is OpenFOAM. We're using the multi-phase boiler simulation model, is with the parameters I just described. And the mesh grading, you can see here, typical mesh from the sides of 621,000 mesh cells. And we do not resolve the boundary layers at the wall. We don't need to do that, but we have a grid that's fine enough to measure the large structures that are generated by the buoyancy-driven flow. Inlet boundary conditions, we just inject air at 1 and up to 23 centimeters per second in the vertical direction. The inlet is no slip. Outlet boundary conditions where we basically just have air at the outlets with outflow condition. And then the walls, not very dependent on the boundary condition, but we have no slip and 0 gradient for the volume, for the void fraction. Okay, for comparisons with experiments, the measurements that we're going to use for validation are done at this height over diameter ratio. The things that are measured experimentally were the void fraction at different radial locations, the bubble axial velocity or vertical velocity. And so we have all the values. We can measure positive and negative values. And we also, as done in experiments, we just look at PDFs also of the positive values. This particularity of the probe, we'll be looking at both of those. And then for the joint public distribution function, again, we're going to be looking at bubble axial velocity. And at the same time conditioned on the void fraction, so we're able to see what's the velocity of the mixture as a function in high void fraction regions and in low void fraction regions. So we have univariate PDFs and joint PDFs. Likewise, we have conditional PDFs of bubble velocity conditioned on void fraction. In the JFM paper from the Grenoble group, they split it into 3 different types of regions. High void fraction or cluster regions where bubbles are moving up at high volume fraction, intermediate regions where the bubble velocity is near the mean, and then regions where there are very few bubbles or voids. And we'll see how those depend on the velocity depends on which region you're in. And likewise, we'll be looking at liquid velocity data. Okay, so in OpenFOAM, the way you get data, you can put in probes, and so we need to put in probes at the same locations as the experiment. So, for example, we have at the location the experimental data was taken, we put in which corresponds to 1.545 meters above the bottom of the column. We put in probes at the center line, and then at 10%, 20%, etc., up to 90% to the wall. And we have probes across here. The probes, then you can take out any data you like, and you could put probes elsewhere, but we're just going to show today data where compared to the experiments. You can monitor things like instantaneous void fraction, gas velocity, and liquid velocity in comparison with experiments. The frequency of measurements for our case was for the CFD code was 200 hertz. That's just a choice. If you go fast, finer, the data are correlated, and if you go slower, you miss some of the dynamics. We kept it 200 hertz, and then we have take data for 50 seconds of running of the simulation. So we'll be looking at that. Okay, just to give you some idea about the bubble size variation. So when we first did the simulations, we thought we would have to worry about the bubble size distribution because the velocity depends on size. But it turns out from the experiments, the bubble size is very well controlled. And so at different gas velocities, these are the experimental data for the mean chord length, which they were able to measure with their probe. And likewise, the solid mean diameter of the bubbles. So what we did in the simulation then is to take the solid mean diameters and fix our bubble size and use a monodisperse bubbles. So we didn't have to account for bubble size distributions. Again, that would only be necessary if there were coalescence and breakage, which there wasn't in the data. So again, the paper that describes how they get the bubble size is this 2022 paper. Okay, so that's the setup of what we're comparing. So one-to-one comparisons with the same flow rates, the same bubble size, and same dimensions. And so here, just so in case you haven't seen what simulations or what the difference between homogeneous and heterogeneous flow looks like, you can see this is the low flow rate case. This is for our simulations. And you can see in heterogeneous flow, once you're up to a certain height, the bubble volume fraction is what we're looking at, changes very little, and it's pretty much the same everywhere. There are a few regions where you get a few bubbles, a few higher values, but the fluctuations are quite small. And then when you cross over to the heterogeneous regime, you start seeing now regions where the white regions where you have relatively large volume fractions, so bubbly flow going up very quickly, and then you start seeing these packets coming down at the wall where the void fractions are small. So it's kind of quite dynamic, and then as you go up, the flow becomes more and more dynamic as you see basically buoyancy-driven flow, where the light flows goes up very quickly and you get very fast down moving flow at the walls. And the movie that I showed you earlier, you could see this too. You can see it's quite dynamically different than the homogeneous case. Here's some comparisons. So there is a movie available as supplementary material in the 2022 paper. So the experiments here for homogeneous flow, you can see there are fluctuations in the velocity, but the bubble volume fractions tend to be pretty uniform. There's some fluctuations, but not large. And then in the homogeneous simulation, you see pretty much the same thing. If you look at the flow, this is of course at the wall, and this is across the center reproduction. But the main thing you can see, the bubbles are mainly moving upward everywhere. There are very few downward flow. In the homogeneous regime. In comparison, if you look at the heterogeneous regime, it's much more violent. It's quite the transition is quite rapid, and you see very, very large fluctuations in velocity, bubble volume fraction. We'll see later it's measured experimentally, but the regions that move up very quickly have high volume fractions, and then the low volume fraction regions get pushed down. And the same sort of thing you can see in the simulations. You can see here that the low volume fraction regions near the wall are moving down very, very quickly. And then near the center and nearly across the whole column, you get very high upward velocities when you have a higher volume fraction. So it's a buoyancy-driven flow where there's segregation due to the hydrodynamics that causes things to become heterogeneous and quite turbulent. Okay, so then some direct comparisons with the experimental data versus the simulations. So again, this is in the heterogeneous regime at 23 centimeters per second. And each of the plots is at different radial locations. So here's at the center line, and then as you move toward the wall, the center line, almost all of the flow is upward, and near the wall you have downflow, so you get some downflow parts. So this experimental curves are in black, and the simulation PDFs are in orange, and you can see that the agreement in terms of the mean and the variance RMS velocities are quite good. See that pretty much all the way across the column. In the experimental data, explained in the paper, they're unable to measure accurately near zero velocity at the probe because the bubble needs to be moving relative to the probe. And so there's, I guess, a blind spot that Mark could probably answer more better than I can tell you, but there's a blind spot. And so you have lots of data when you have zero relative velocity. And so you can see in the simulation, of course, we can measure that. But outside of that, on both sides, you still pick up the fluctuations outside the mean flow data. If you look at the average velocity, so this is again at 23, and then the velocity of the bubbly phase as a function of distance from the wall. The green dots are for the measured values for the experiments, and then the flow code gives you the blue lines. We took an extra point that wasn't measured just to get closer to the wall, but you can see the agreement is pretty good going across in terms of the predicted mean velocity. And then if you take just the upward velocity, so you use just the part of the probe that measured upward velocities, and we can do the same filter our simulation data, you can see also you get good agreement between the two. RMS velocities, now looking at fluctuations. An interesting thing here is that basically the fluctuations are independent of the location. On the previous slide, you can see there's a mean upflow in the middle, and there's a downflow at the wall, which is expected because of it's a closed system. But the RMS velocities you can see are nearly constant. So again, experimentally they find to be about 0.8, and we're slightly larger at above 0.8, but the agreement is the same type of agreement with nearly constant values. And then likewise for the upward velocity, we have a few more probably than the probe doesn't allow. That wasn't measuring near zero. So the trends are quite similar. Here are volume fraction measurements. So again, the probe also is able to measure the volume fraction at each location. And we can see here the simulation versus experiments there's actually quite good agreement for bubble column measurements. Oftentimes, when you don't have homogeneous conditions or uniform bubble size conditions, you get very different volume fraction distributions due to the fact that big bubbles rise faster than small bubbles. But here we can see carefully controlled experiments, and using the same conditions for the simulations, we get good agreement between the two. You can rescale here at dividing by the value at the center line, and that's what's done here. And it's compared to a correlation, which was in the paper 2006, which was compared to in the experimental paper. So we did the same comparison. But overall, the volume fraction predictions are quite good with the experiments. Okay, the next comparison we make the comparison with the liquid velocity distributions. So here the agreement is not quite as good. In fact, for the liquid velocity and the bubble velocity, we find actually the PDFs to be they're quite correlated. So if you have low regions with high liquid velocity or correspond to nearly the same velocity minus the slip velocity for the liquid, and so we get a wider spread. I'm not quite sure. Trying to explain this, we probably talked to Martin about it, but I suspect it has to do with the probe. Maybe the probe is measuring only far from bubbles, the locations of the bubbles where we're measuring. We have values at the same right at the bubble location, so we get more fluctuations. The average values are fine. The average values are well predicted, but the fluctuations are different in the two cases. So that's left to be explained when we write up the paper on the comparison. Okay. One thing that we were very interested in doing is comparing the joint distributions between the bubble velocity and the void fraction. So in the literature, there was up to the Grenoble paper, the FM paper in 2023, we never had any data that gave us correlations between the local volume fraction and the gas velocity at the same location. We suspected, of course, that this should be the case. There's a strong correlation between the volume fraction, so regions where you have almost no bubbles have lower velocities, upward velocities, than regions where you have lots of bubbles. And so you can see at the center line, and then if you go across, you have a very strong correlation, nearly linear, between the two variables, and a fairly widespread. And so from these data, we can then compare with the data from the Grenoble group, where they looked at conditional velocities for different types of bubbles, voids, clusters, and intermediate regions. Likewise, if you look at the liquid velocity, the correlation is also quite strong from the simulations. And again, that's where you have lots of bubbles clustered together at a high volume fraction. You get high upward velocities for both the liquid and for the gas phase. Okay, so we wanted to compare directly with the 2023 DFM paper. In that paper, they compare conditional velocity PDFs, which on the next slide, with three types of different regions or different regions of void fraction. So in their figure 8 of their article, they identify basically three regions, and they can do this from their probe. In their fiber optic probe, they're able to see regions where you have lots of bubbles coming through the probe and measure the velocity, and then regions where there are very few bubbles and still measure the velocity, and then intermediate regions near the mean void fraction. So in our data, of course, we have data for all of the values, because we can with continuous distributions, and so we need to basically identify what we're going to call as clusters, what we call intermediate region, and what we call void region. So it's a bit subjective in the sense that if you can make small changes, but in general, it's not too sensitive to where you cut off for the intermediate regions and the void regions and what you call clusters. So we did that, trying to follow what they did in their paper. And so here now we're looking at conditional bubble velocity distributions for three ranges. So the range above 0.26, we have what they called in their paper clusters, so lots of bubbles in a high volume fraction, and you can see comparing, we get very good results for the comparison between what was seen experimentally, which is the black line, and then the blue line, which is from the simulation data. And you can see the velocities are relatively high, nearly mean value over 1 meter per second. In the intermediate regions where you're near the mean void fraction, we have lots of data there, so we can split that into a fairly tight region. And you can see, again, we get a good agreement with what they called their intermediate regions, where, again, the mean volume is, of course, mean velocity is lower, and we get spread towards the lower side, but we get good agreement on the shape of the PDF. And then finally, in the void region, so regions where there's very few bubbles, so very relatively low void fractions, you can see there's a comparison between the experiments with the black curve and the yellows for the simulation data. So again, the trends are quite well predicted by the model. For the liquid velocity, this is the conditional liquid velocity. There we had just data for liquid velocity of above 0.6. So the faster moving, so this should be in regions of higher void fraction. And so we did the same. We took only the regions where this is high void fraction, so this is regions where there's very few bubbles. And we can take the same data from the simulations and compare with the experiment, and the general trend. You can see the mean velocities are well predicted. And here the spreads are better than in the previous slides. We get closer predictions than in the case where we had conditional at high void fractions for the bubbles. So this kind of does well in regions of low bubble concentration. So we have just mainly the liquid flow. It's easier to measure the velocity distributions, and so the agreement tends to be better. The issue with the probe at 0 is still there, but we still get the spreads are wider than we saw for just the unconditional data. Okay, then we looked at a few other things from the simulations that weren't done in the experiments, were reported simultaneous. So we can take, for example, the joint liquid and gas velocity distribution. So you have gas velocity on the vertical axis, and then on the x-axis, we have the liquid velocity. If you look here, 0, 0, that would be, in each case, there's a slight offset. So basically, we get a linear plots between the two. So there's a linear growth. So a linear correlation between the two velocities. And 0, 0 is, if you go up from there, you get the slip velocity for the bubble, gas bubble slip velocity. So in each case, you can see 0, 0 is slightly higher. So basically, if you know the slip velocity, then there's a linear correlation between the two velocities. So there's this offset in each case by the slip velocity at that location. I don't know if there's data for this, or maybe Martin can tell us, or we plotted these because we suspected that the slip velocity is pretty much a constant, and then it's just a matter of a linear and strong correlation between the two velocities. Okay, then to finish up, to summarize, so we have what we feel to be well-resolved flow simulations of a two-fluid model. We did different grid sizes. The grid size I showed you is one of the smaller ones. You can go smaller, but it doesn't really change the statistics because most of the velocity statistics and volume fraction statistics are much larger length scales in the grid. We collected probe data at the same locations as used in the experiment. And then we did direct comparisons between bubble velocity distributions, the mean and the RMS values, and we found good agreement with the experimental results. We also did comparisons with the mean void fraction, and that also were in good agreement with the experiments. And then interesting for us was, because we didn't ever have this type of data before, were the conditional bubble velocity distributions. And so we were able to generate those from the simulations and compare them to the experiments for the first time. Finally, we found what I showed you on the last slide, the linear correlation between the bubble velocity and the liquid velocity, which, if data are available, it would be interesting to compare that. In future work, we're going to continue to look at different superficial gas velocities for the other cases that are available for the Grenoble data. We'll also look at the more velocity distributions. There's some more data available from the Grenoble papers. We'll do more comparisons. And then there's some other things we've been working on, different closures for the two-fluid model. For example, we're going to add those to the OpenFOAM model in OpenFOAM, and then just do retestings. Okay, so that's all I have, and thank you for your attention. I'd be happy to answer any questions.
So, thank you very much, Rodney, for this interesting seminar. Is there any questions in the room?
So,
yeah, please.
May I have a question?
Yes.
Yeah, Rodney, thank you for your talk. And since the breakup or coalescence between bubbles was not taken into account, what do you expect this linear correlation between the velocity and bubble voids, whether or not it will be changed if you will take into account this breakup or coalescence phenomenon?
Yes, I think, for the data for Grenoble, I don't think it'll make any difference because there was basically no breakup in coalescence. And in fact, I visited Grenoble and looked in their column to make sure that was true. Martin assured me that the water in Grenoble does not allow for this. But in general, it's a good question. I mean, a lot of problems with comparing with bubble column simulations is that you do get a lot of coalescence and breakage, and in fact, it becomes heterogeneous much earlier because you get coalescence. And if you condition on bubbles, if you condition on the bubble size, I think the slip velocity would be the same constant. But if different bubble sizes, for example, larger bubbles rise much faster than the smaller bubbles. And so if you had data that could condition on size and velocity, I think you'd probably see it for the constant size, but not not when you have different sizes, right? In fact, if you look at the models, they have the drag coefficient. The drag coefficient depends on size. And so it's if you just look at the drag, it says that if a bigger bubble will have lower drag, and so they're going to go up faster. So,
and So the size is less than Kolmogorov scale, yeah, here.
Oh, no, they're bigger. They're much bigger. I mean,
Much
there's
bigger.
no shear generated turbulence here. So it's
Uh-huh.
already the buoyancy-driven turbulence. So it's basically driven by the size of the cluster. So I suspect the Kolmogorov scale in the liquid phase is much smaller than this. Although we're not resolving that because we're basically resolving interval scales and inertial range scales that are generated by the turbulence that are generated by the bubbles. So.
Yeah, and the last question, I'm sorry. And what about the moments of bubbles velocity?
Mm-hmm.
So do you, in fact, whether or not all those moments are connected to the breakup phenomenon?
Well, I mean, we have codes that do bubble size distributions and velocity with breakup, and we didn't need to use them here. But I certainly the local turbulence are going to be connected to the bubble size distribution because the bubble breakage is going to be dependent on local turbulence structures. And then likewise, coalescence will also be controlled mainly by kinetic coalescence either. Although in bubble columns, a lot of coalescence is driven by just velocity difference due to size, or it's in the wakes. They coalesce in their wakes, but the breakup is definitely will depend on the local turbulence structures. So there'll be some pros. I mean, in this case, the bubble velocity distributions are pretty close to Gaussian. I mean, there are some tails towards the lower velocities, but in terms of I think it's very similar to other buoyancy-driven flows, the types of bubble velocities the bubble velocity PDFs we see. So.
Okay,
Yeah.
thank you.
Yeah.
Okay, Michael, is there any other questions? I think Alan has a question.
Oh, no mic.
So you're muted, Alan. Otherwise, you can write it on the chat. But vale.
This time is okay? Okay.
Yes.
No, just one comment on Bruin technique. We have a problem with the Pavlov technique for the liquid velocity because we have a difference in height about 1 centimeter between the two orifices.
Okay.
So that means we filter events at this size. So hopefully we do not change too much compared to the statistic we found. So that's good, but we have also this problem near zero. The other question is, have you tried to compare the size of the structures with what we found in experiments?
That's on our list of things to do. So the simulations we just finished doing the first round. So we were also going to look at the statistics of the structure sizes. So and all the things that are in your paper. That's Martin has been very generous giving us data. So we have all the data. And so the next thing would be to consult with you and Martin about what are the things we should be extracting to look at size. We look at them side by side, the simulations, the animations, they look very similar in terms of the length scales of the structures, but we like to get more quantitative data for that.
Yeah, I'm quite interested in the shape of this structure.
Right.
Because for us, it's a mystery.
Yeah, okay. So we want to look at that too. Yeah. And so, I mean, we can get all that data. So we have to define how we define a structure and then look at the shape. Just make sure it's all consistent with quantitative measurements. Very nice data in any case. So for the first time.
Any other questions?
Yes, I'd like to ask a question.
Sure.
Hi, Rodney.
How you doing?
Oh, just fine. Way into retirement.
Oh, yeah.
About 12 years now.
Wow.
So I'm trying to keep up with things. So my question relates to the possibility of more reduced forms of modeling of this flow. in the sense of how close is it to being, for practical purposes, laterally homogeneous? For instance, suppose you had simulated it in a cuboidal box with lateral periodic boundary conditions. Do you think the results would be much different?
I think we've done simulations like that already, and we find that if the column is wide enough, then the main part in the center has very similar statistics. I mean, at the bubble column, you get the downflow to walls, and so there is a confinement effect. But I think if you look at the center line, the statistics are actually very similar in terms of the structures that you see. And maybe you get slightly larger structures because, well, depending on the box size you use, but you get because there's no confinement effect with the downflow. But I think, for example, when I showed the RMS velocities, the independent of the column width, that's kind of an indication that that part of it, at least, that the mean velocity statistics are strongly affected by the walls.
And so, as a practical matter, do people make that idealization when they're working practical engineering situations?
Yes. I mean, the other thing you could try to do is a turbulence model, right? So you don't have to use a grid. But that's like any buoyancy-driven flow where you have structures that develop and then the integral scale increases. So that's a more difficult thing to do. But there are plenty of engineering models where they basically use a turbulence model that figures everything out. And then the question is, do you get the right dynamics for that? So it seems like at this point, you kind of have to do a large eddy-like simulation where the grid, it captures at least the structures, the scale of the large structures that are generated by the flow. Maybe not all the way down to the smaller structures, but at least the larger ones that are generated. It's kind of like pool fire simulations that were done. Remember, you were involved in those with Phil Smith. So if you had to find enough grid, you could capture most of it. But there's a characteristic length scale for the plume sizes that are going up that you have to get the cascade back. So.
Okay, great, thanks.
Good to see you.
Good seeing you.
Thank you. Any other questions? You can also write them in the chat eventually. Ron, I have a couple of questions while we wait for someone else. So the first one, I'm sure you thought about this. It's very impressive, no? When you show the time resolved heterogeneous regime that we see the structures, as we see in the experiment.
Right.
But as you saw, we discussed our boundary condition, and the free surface is not air; it's actually foam.
Yeah, so that's my. Yeah. I have a model that reproduces foam. In other words, it has a. Basically, what we're missing is the volume fraction. There's a maximum volume fraction, right? So above a certain volume fraction, you become a foam. In the two-fluid model that we're using now, there's no maximum on the volume fraction locally, but you actually if you put in a model for the pressure. In the two-fluid model, it'll block the maximum value at least 0.63, and you'll form a foam. So that's what that's on my list of things that I've been at the postdoc to do.
Do you think the foam will play any effect on the dynamics?
I don't think so, because it's going to damp out the top. It'll keep it but it'll be like a plug it's very light, right? It has no real weight and no real pressure, so it's just going to kind of stop the stuff from moving once it gets to the foam. The volume fraction's high enough, yeah. But below that, where we're measuring the probe, I don't think it'll have any much effect for me. And
then you may be aware that our colleagues in Prague are playing with the startup and shutdown regimes of the column. You think that your model can be used to?
Yeah, I think so. Yeah, there shouldn't be any reason why. Yeah, because we have a startup regime where you get a plug moving up, so it'd be very interesting to look at the dynamical regimes. Yeah, but there's no real reason you can't do that. So.
Okay, good. But is there any other questions? Any other comments? Okay, so thank you again, Rodney, for this very nice seminar. Thank you, everyone, for being here, and so hope to see you soon.
Thank you. Yeah.
We'll talk to you soon again. Yeah.
Bye bye.